o nosso próximo colóquio. Já começou? Então, bom, antes de mais nada, eu queria agradecer a todos pela presença hoje. O nosso palestrante é um colega nosso do departamento, o Matthew Luzum. Aliás, deixa eu cortar o som aqui. E certamente ele dispensa apresentações para o nosso público local, mas deixa eu fazer um breve apanhado do currículo dele. O Matthew fez o seu doutorado na Universidade de Washington em 2009, depois fez vários pós-docs. Eu encontrei algumas referências a Saclay, a Universidade de McGill, ao Lawrence Berkeley National Laboratory, nos Estados Unidos, e também em Santiago de Compostela. E desde 2015 ele é professor do nosso departamento, sendo atualmente professor associado. E essencialmente as áreas de trabalho onde ele tem atuado envolvem física hadrônica, o famoso plasma de quarks e gluons, QCD e dinâmica relativística viscosa. Eu vou passar a palavra ao professor Matthew, só lembrando antes que na próxima semana, na próxima segunda-feira, nós teremos mais um colóquio, também na área de física de partículas, do Diogo Boito, que é atualmente da Universidade de São Carlos, do IFISC, e está atualmente na Universidade de Viena. Ele também vai falar sobre QCD Parameters for Standard Model Precision Physics. Então, muito obrigado a todos e ao Matthew mais uma vez. Eu passo a palavra, então, a ele para o início do nosso seminário.
Obrigado pelo convite, pela introdução. Vamos compartilhar.
A propósito, Matthew, se você desejar falar inglês, não tem nenhum problema, viu? Você que escolhe.
Que bom. Com certeza. Gostaria de apresentar em inglês. Ok. Pode ver os slides?
Sim, sim.
Tá tudo bem? Ok. Okay. So thanks again for the invitation and for the nice introduction. So today I thought I would present a few results from these works here, which are some recent results for extracting properties of the quark-gluon plasma from experimental measurements. So to do that, I'll give a pretty brief introduction. But I should mention, I think it's fine if anyone stops me and asks questions anytime during. I don't think that will cause any problems. So I can always add more details if I'm skipping too much. But some introduction motivation, which is studying the strong interactions at high temperature, and doing this through heavy ion collision experiments. And so the main part of the talk are these two chapters here, 2 and 3, where I want to give a couple of examples of phenomenological work. Many of the things, most if not all of the things that we would like to know about strong interactions in this particular regime, these temperature and energy scales, are difficult or impossible to calculate. And so a very important part of this experimental programs is phenomenological studies like this, to see what kind of constraints we can put on theory from the experimental data. And so here are a couple of examples that have that study two different types of properties of the quark-gluon plasma, but also have fairly different approaches, sort of a more traditional approach first, using sort of intuition to try to simplify the problem as much as possible and isolate the properties that we want. And next, a more, in this case, a bit more brute force type of approach, yet more systematic. And that will give me a chance to talk about Bayesian analyses, Bayesian inference. Where are we? Okay, so start with the introduction. Here's some slides I made for the Institute colloquium, so I'll go a little bit quicker through it, but The idea here is just to get an idea of the kinds of temperatures we're talking about. I said we want to study very high temperature matter. And so basically matter above 200 GeV for the particle physicists. But this gives you sort of an idea of where that sits compared to more familiar things in SI units. Okay, and this is the temperature where confined matter transitions to deconfined matter into a quark-gluon plasma. This slide is basically just to say that at these extreme temperatures, the dominant contribution, the dominant force governing system and the properties of the system is the strong force, the strongest of the standard model interactions, strong interactions, of which the fundamental constituents are quarks and gluons, and interact in order to form things like protons and nuclei. So that's what we want to study. The fundamental theory of the strong interactions is quantum chromodynamics, so we know the fundamental theory. QCD, it's a non-abelian gauge theory, where quarks and gluons have a color charge. They interact by exchanging gluons. And the important thing for our purposes is that the coupling runs, meaning is the energy scale or momentum transfer in the interactions between these quarks and gluons changes, the strength of the interaction is different. So at very high energy, high momentum, or short length scales, there's asymptotic freedom so that the coupling goes to zero. It's very small, but that also means that at lower energies, the coupling gets large, very large indeed. And this is what causes what's called confinement, which is the observation that we do not see particles with a color charge in ordinary environments. But quarks and gluons actually only exist in color neutral bound states called hadrons. So ordinary matter is confined, but if you go the other way and go to high enough energies, high enough temperature, for example, we can encounter a system where these color neutral hadrons, like protons and neutrons and so on, are no longer the correct degrees of freedom. And the quarks and gluons themselves are no longer confined, and they are now the correct degrees of freedoms with which to describe the system. So that's the main goal here, is to study, understand the strong interactions in this regime, in particular for today, this quark-gluon plasma and its properties. So in order to study this experimentally, we need, this is an extraordinarily high temperature. So we need to get an extraordinary amount of energy into a very small space. So to do that, of course, we need colliders. And results that I'll use today are from the relativistic heavy ion collider, which is in the US, and the Large Hadron Collider in Europe, in Switzerland and France. And the idea is to take the nucleus of heavy atoms, for example, gold or lead, accelerate them to ultrarelativistic energies and allow them to collide, and hopefully create this high temperature quark-gluon plasma. And then perform measurements at the end of the collision to try to extract whatever properties we can. So that's the main setup, main motivation. To understand these results and how they're obtained, it's useful to step-by-step go through how we see the temporal evolution of one of these collisions, these heavy ion collisions, both to understand the type of physical processes that are involved, but also to get a sort of a feeling for how complicated it can be. It's different stages, and each one of them can be nonlinear, non-perturbative, which give an idea of how complicated of a task it is to try to extract the information that you want from the final observables. It's not necessarily as clean as you would like, as you see in some other types of measurements. So to start out, you have just the two nuclei that have not yet collided, and so this involves knowing the structure and properties of ground state nuclei even before any collision happens. Then there's the initial collision, the initial scattering between the constituents of these incoming nuclei. Which involves, low x, part of the wave function of the nucleus, but also it involves not only, high momentum transfer scatterings that create jets like you'd study in a lot of high energy collisions, but if you want to know how the bulk of the system behaves, you need to know how the bulk of the particles are produced. So this can also be rather complicated and not necessarily amenable to perturbative calculations. And then after the initial scattering, there's some period of time. So after this period of time, the system behaves like a relativistic fluid, but there's some finite period of time where the system has to evolve into a state that can be described that way, which here I write as equilibration. We're learning, of course, now that that's maybe too strong of a statement, but fluid dynamics actually has a rather wide range of applicability. This doesn't necessarily require being as close to equilibrium through thermal equilibrium as you naively would think. But nevertheless, there's some complicated, so in this case, a bit far from equilibrium, many body physics processes that happen that bring it towards something that can be described as a fluid. Finally, the bulk of if you want to simulate a collision, the bulk of the time evolution is taken up by this part here, where the system expands and evolves as a relativistic fluid, a relativistic viscous fluid, which can encompass both a confined and a deconfined phase. So the highest temperature, you have a deconfined phase. As it cools down, it converts into hadrons as the correct degrees of freedom. But in both cases, it potentially can be described as a fluid. So first quark-gluon plasma, then deconfined hadrons. At some point, you have to switch from if you're doing a simulation, you have to switch from a fluid description to a particle description. And so once you make that transition, then you describe the system as, this has to be after the phase transition, so that you can describe the system as only hadrons. You can allow them to scatter using some kinetic theory. And eventually they decouple, stop interacting, and they stream to the detectors. That's just kind of an overview of how we see one of these collisions evolving. The important thing here is that we can simulate all of these things. We can perform simulations of the collision, but these simulations involve models and they involve parameters that are not necessarily able to be computed reliably from first principles. And so doing phenomenological studies to restrict these parameters, these properties, is at least one important part of this program in order to inform theory and extract properties of the system. Okay, so with that introduction, oops, I don't have a clock nearby. It's my watch. Just keep track of time. Let's talk about two different recent works, recent approaches for trying to extract properties of the quark-gluon plasma from these heavy ion collision experimental data. So first, let's talk about thermodynamics. So equilibrium properties of the quark-gluon plasma, equation of state. And through this equation of state, we can essentially count degrees of freedom to verify whether indeed we have a deconfined system where the color degrees of freedom are liberated compared to a confined system where the color degrees of freedom are hidden and the relevant degrees of freedom are only these color neutral hadrons. That's the idea. So first the question, can these thermodynamic quantities be computed from first principles in theory? So there's a couple of answers. First, because of this asymptotic freedom, because the coupling runs in QCD, as the temperature gets very large, if it goes to infinity, the coupling goes to zero. So the coupling at very large temperature becomes very small, and you can in fact calculate thermodynamic quantities using perturbation theory, perturbative techniques. However, for our cases, that's not actually very useful, because in the temperature regime, that's both accessible experimentally, but also the interesting temperature regime around this transition temperature where lots of interesting things are happening in QCD. The coupling is no longer small. The coupling can in fact get very, very strong. And so the system can be very non-perturbative. However, luckily, or well, very nicely anyway, you still, even in this non-perturbative strong coupling regime, it is possible to calculate thermodynamic quantities. And you do this using numerical techniques, specifically lattice techniques, lattice QCD. You discretize space and time, and you do numerical computations. As I said earlier, that most of the time you cannot calculate things from first principles. This is not only one counterexample, it's perhaps the only counterexample in our field where you can really reliably, from first principles, compute things, specifically equilibrium properties at vanishing chemical potential. It's very well suited for these numerical techniques. And so then, of course, you might ask, why do we need to do a measurement? But of course, it's still important to verify these theoretical calculations with phenomenological measurement of these properties or verification. So that's the idea here. So here's an example from, I think, still the latest. I mean, the most up-to-date calculation. I think the final calculation, fully continuum extrapolated and everything, of the QCD equation of state. Here specifically is the entropy density and the energy density, suitably scaled to get a dimensionless number here. And just as a reminder that these things are then proportional to the number of degrees of freedom in a classical thermodynamic analysis. And so that sort of tells you why you see what you see here, that at low temperature, because the color degrees of freedom are confined into colorless neutral hadrons, this entropy density, the scaled entropy density, for example, is very low. But at very high temperatures, you have a deconfined quark-gluon plasma, so that the number of degrees of freedom is much larger. And so you have a big increase in the entropy density of the system. And so in between, you have this transition, which technically is not actually a true phase transition. It's a smooth analytic crossover, but it's still a rather stark change in the number of degrees of freedom as the system becomes deconfined. So this is what we see, but now we want to ask the question, can we see this experimentally? Can we confirm experimentally this deconfinement through some way of detecting the color degrees of freedom? So that's what I want to do with this work, which here is just an example of a recent review of some of the big questions that still remain in the field, and this was actually listed as one of them. So reading here, can we obtain an experimental determination, even indirectly, of the temperature of the matter produced in a heavy ion collision at a time when we can also determine its energy density, or for our purposes, the entropy density? If we could obtain an experimental determination of the number of thermodynamic degrees of freedom the quantity whose increase represents liberation of color. So that's the goal of this this part of the talk here. Can we do this? Can we do this experimentally? So what I will end up doing is extracting the value of the entropy density at one particular temperature. And there's always a little bit of skepticism about something like that, because the system, as you saw before, is very complicated and has evolved. It expands and cools in a very non-trivial, potentially non-linear way. So it experiences many different temperatures at many different points in space-time, and then it evolves in a complicated way. So first, I like to give a little example that sort of intuitively tells you a little bit about why it is possible to extract such a thermodynamic relation, such a simple thermodynamic relation from a evolving dynamic system. So this is a simplification, and none of these assumptions are made in the actual analysis, but it does illustrate, I think, important parts of the analysis about why it works, in particular the role of conservation laws. So let's just go through this thought experiment. Let's imagine we have some thermal system drawn over here with some volume, some total energy, and some total entropy. And it's a thermal equilibrium at some initial time. But then after that initial time, the system expands into the vacuum, but it does so as a fluid, in particular an inviscid fluid, no dissipation. So in that particular case, not only is energy conserved, but in the limit of ideal hydrodynamics, the entropy is also conserved. So the initial energy and the initial entropy is equal to the final energy and the final entropy. So in principle, we could reconstruct the initial thermal state with the following information. First, the final number of particles. If we also knew the energy per particle. We could also just say measure the energy, but this mimics more closely what we will actually be doing. So we have the final number of particles, the energy per particles, and we have the initial energy, because it's equal to the final energy. If we know the entropy per final particle, along with the final number of particles, we have the final entropy, but that's also equal to the initial entropy. So we have that. But then we would still need the initial volume in order to reconstruct thermal state. But if we have all of that, we can do it without knowing anything else about what happened between, just this assumption of fluid expansion and knowing these final observables, even if it's highly non-trivial, highly nonlinear fluid evolution. So hopefully that gives at least some intuition. Okay, so this work actually started a long time ago in some sense. So way back in 1982, which, believe it or not, is almost 40 years ago, there was an idea from Leon Vanov, which is the following. So consider the transversal momentum, which I haven't defined before, but it's basically just the component of momentum which is orthogonal or transverse to the beam direction, which is something that's easily measured. The idea is that the mean transversal momentum, the average transversal momentum that a particle has, is a measurement of is a fraction of the energy per particle. And also the temperature should also be a fraction of the energy per particle. So the idea is that you get a measure of temperature from the mean transverse momentum. Next, at a fixed volume, the number of particles is proportional to the entropy density. Here are the CH transfer charge hadrons, for those who care about the details, but this is basically the number of particles at the that you measure in a collision system. And so the idea was that if you vary the collision energy, change the collision energy, and you plot transverse momentum versus particle multiplicity, you in fact get a measurement of temperature versus entropy density. So in the end, it's a good idea, but there's some complications such that it's not quite so simple in reality, which explains why it was only 40 years later that we made some progress with all of this. But that still gives some of the basic idea. So we will try to obtain some notion of temperature from the mean transverse momentum, and we will get an entropy via counting particles. That will still be part of our analysis. So what are some of the complications? So in particular, we do not measure an isolated system. What we actually measure is some slice of the system. So the detectors have some finite coverage in this perpendicular direction of the system. So you can think of the fact that we observe what comes out of some slice of the fluid near what they call mid-rapidity. So basically near perpendicular to the beam here. And so it's not isolated. So what actually happens as a system, you can see the system expands longitudinally. So once these two nuclei collide in this longitudinal direction, the system, the edges of the system continue to retreat, and this whole system stretches. And so what happens in a particular fixed region in rapidity is that the energy decreases as the system expands. The system is doing negative work on the system. At early times, the energy of this slice of fluid goes like time to the 1/3 power. But then finally later, due to transverse expansion, pressure continues to decrease and the energy converges to some final constant value at a far later time. And so because of this, this mean transverse momentum does in fact correspond to some sort of, we will see temperature, some sort of energy and entropy of the system, but it's the final energy and entropy which is different from the initial because of this longitudinal cooling. Okay, so understanding that, we can get to the actual analysis to see how it works. So the first thing we do is we define an effective temperature and effective volume. And these are completely defined quantities, not you define them any way we like. It's not a measured or derived quantity at this point. And so what are they? The temperature and volume, the effective temperature and volume are the temperature and volume of a uniform fluid at rest with the same energy and entropy as the collision system measured at the end. So after this freeze up, this decoupling. So at the very end, in some finite region of rapidity, we measure a total energy, measure a total entropy. So those things we can measure unambiguously. And then we define these two things as the temperature and volume of uniform fluid at rest with that energy and that entropy. With, so in a particular model, given some input equation of state, these things are uniquely defined. So in a given simulation, these things are uniquely defined. As such here. So total energy is just the integral over the freeze-out surface of the energy. Same with the entropy. And thermodynamic relations give you a unique value for these each of these quantities given the input energy and entropy. So that part's just a definition, at least in simulations. The non-trivial part is this statement here that I will show that I can obtain the effective temperature and, very importantly, the entropy density at that temperature. So do simulations. So just emphasizing again that I'm not making any of the assumptions that I made in that simple thought experiment. We're just going to verify everything in simulations, varying all of the uncertain parameters to make sure that this works. And so what we observe is the following. So we calculate the effective temperature. So this can be computed straightforwardly. Again, is defined by the total energy and total entropy at the end. Here it's plotted as a function of centrality. You can see several curves here. This just gives an example of varying parameters. Some of the most important are the viscosity of the fluid. So the solid line, for example, is ideal hydrodynamics with zero viscosity. And this dashed line is if you have a non-zero shear viscosity only. The dotted line is shear viscosity and bulk viscosity. Just to give you an idea that some of these parameters, unknown properties of the system, do affect the value of its effective temperature. Then in all of these cases, we calculated the mean transverse momentum, which is an independent quantity in principle of the final particles, the final charged hadrons. You get a curve like this, which you can see is actually quite similar, which is not a coincidence, because indeed we find that to a very good approximation, the mean transverse momentum is always proportional. It's always a unique constant proportion of the effective temperature. So this, in fact, is the most non-trivial part of the reason why this all works is because we can reliably get this effective temperature via the measured transverse momentum. So even though each of these quantities depends on unknown things, such as viscosity, they're always proportional to each other. They always change in the same way. This is valid for any collision centrality. It's insensitive to parameters. Okay, so we can actually do this now directly from experimental data for the mean transverse momentum of particles coming out of a collision, which is this value, for example, in central collisions, which then gives us directly an effective temperature, which is about 222 MeV. Or in terms of Kelvin, like this. Okay, so we have an effective temperature. Now, what I still promised is we need to figure out how to extract the entropy density of an equilibrium system at that temperature. So that's the next step. So first we need the total final entropy. So this we can leave to others. So these authors here, not too long ago, did a very careful analysis to determine the average entropy per particle produced in this type of collision. So what we need is entropy density, which is the total entropy divided by this effective volume. So first, the total entropy we can get from the entropy per particle, which is known. And of course, the number of particles also known. Also, that's easily measured. And so we can directly calculate the total entropy. The effective volume, on the other hand, actually cannot be measured. It must be estimated. And in fact, this gives the largest source of uncertainty in the final result. But at least being conservative, we can do this calculation. So we can compute the effective volume in simulations. non-trivially. Experimentally, we have to estimate what it is. So here's some computations of the effective volume in simulations. And you can see that it follows fairly closely to this, which is this R0, which is the initial transverse size of the system, which is basically given by the transverse size of a nucleus. And so we can estimate this effective volume with this type of formula, taking the radius of the nucleus as R0. In doing that, we can obtain now from this total entropy and this calculated effective volume, we get an entropy density, which is about 20 Fahrenheit to the -3. Okay, how does this compare to calculations from first principles, from lattice QCD calculations? Here's our result. So if you divide by the temperature cubed to put it on the same plot here, you get this result here, which shows up right about here. And remember, we're comparing it to this yellow line, which is the entropy density. So a couple of things to point out. It's compatible with the calculation. So we're consistent with what we believe from the fundamental theory. And also, it confirms a very large number of degrees of freedom. It's inconsistent with a purely hadronic system just by counting degrees of freedom, just by the large value, this entropy density. And so finally, we have a fairly direct observation of deconfinement in this system. So I'm actually going to skip through this for time because I still want to talk about other things. That section was basically by varying the collision energy, you can extract the speed of sound of the system, which is defined here, which is also consistent with first principles calculation. So for this part, the main point is just that it's possible to reconstruct thermodynamics of strong interactions in this particular temperature range using the measured mean transversal momentum and multiplicity. The results agree with calculations from lattice QCD and confirm that a deconfined system is created in these collisions. Okay, so I still wanted to have a little bit of time to give another type of analysis. In particular, fairly recently, the field has begun to use methods of Bayesian inference to give a sort of more systematic approach to parameter estimation. And so I wanted to talk a little bit about that in general and the recent results. In particular, to study, instead of the thermodynamics, to study the transport properties, transport coefficients of the quark-gluon plasma. Things like viscosity, shear viscosity, and bulk viscosity. So these transport properties, these are not equilibrium properties. These are properties of the system that are perturbed from equilibrium and then evolve back toward equilibrium. So it actually involves real-time dynamics. And because of this, it's not very amenable to lattice methods. And it's not possible to calculate with lattice QCD. And because of this, because it's also in a potentially strong coupling regime, there's really no reliable first principles calculation possible. So this is more of a traditional case in this field that it's very difficult to do, robust first principles calculations, and there's a lot of approximations and modeling involved. And so this is where phenomenological studies become very important. to sort of inform models and theories that people develop. So up until this point, before this work, there's had been lots of phenomenological studies on this, and they've made a lot of progress. There's really been a lot of, especially qualitative, but even quantitative progress. Determined, here I say we determined essentially the order of magnitude. So to some extent, we know how large the viscosity is. Enough to know that the quark-gluon plasma near the deconfinement transition is a very strongly interacting system. But now we are getting to a point where we would like more precision. And so this requires a systematic approach. And so this is where this Bayesian inference comes in. So what is this? What is Bayesian inference? For those of us that don't know, it's becoming more and more common in many parts of physics. So perhaps you're already familiar, but I want to give a little bit of an introduction anyway. For those of us for whom this was fairly new. So the calculation that we are most used to, is the easiest to do, not necessarily easy, but easier, is that if we have some model that depends on some parameters, we do computations of observables in that model. And so we can predict, based on some point in parameter space, what should measured observables be. But what we are more interested in is sort of a backwards, the inverse of that. That in the context of some model, of course, we always have to have some physical model in mind. But given some measurements that have already been made, what does that imply about the values of these unknown parameters, these physical properties that are represented by these model parameters? So we want to estimate these parameters. So we want to do a parameter estimation to answer the question of both what parameter values are compatible with experimental data and with what confidence. We want some kind of notion of uncertainty as well. So this is the type of question that can be answered. One way of answering this question is using Bayesian inference. So what does this mean? All right, so the beginning, what we do is we associate with a set of experimental data, here represented by D, and some set of parameters, P. Each of them are associated individually with some multidimensional probability distribution. And Bayes' theorem is a very simple expression, so I'll show it right here, which relates conditional probabilities. So just a bit of notation, this means the probability of D, assuming that P is true, or the probability, this particular example is a probability that measurement data will take the value D, given some parameter values P. And so this Bayes' theorem is just two different ways of writing the probability that both D and P are true. So one way of writing it is it's the probability of D given P times the probability that P is true. So this whole thing is the probability of both D and P being true. But that's also equal to this other way of writing it, the probability of P given D times the probability of D. So that's Bayes' theorem in general. In our particular case, where this is data and some parameters of some model, give these names to each of these things. This is the prior probability for the parameters. This is called the likelihood. So given some parameter, what is the probability that the data, the experimental measurements will show some value? So this is the likelihood. This is something that you can calculate in your model. And this is equal to what's called the evidence, the Bayesian evidence, times the posterior. This posterior distribution is what we want to know. Given the experimental data, what is the probability that the parameters take on a certain value? which is proportional to the prior times the likelihood. It also involves the evidence, but very often we only care about, relative probability, like which is the most probable parameter point in parameter space and how fast does it fall off. So at the very minimum, what we're going to need is to compute this likelihood from model calculations. But we also need to assume some prior probability. So I'll talk about each of these in the next slides. So first, the likelihood. That's fairly easy to understand. It's the probability to observe some data given some parameter values. So given some parameter values in some model, we can calculate model predictions. And we can compare it to the data, and we can define a probability by calculating the deviation of the model prediction from the data so that you have some exponential fall off. We define this chi-squared, which is sort of the added in quadrature, the difference between the model and data, but divided by the uncertainty. So that's the sort of intuitive way of seeing what we're doing. So that if there's a very small difference between data and model, it's a very probable point in parameter space. If there's a larger difference, it's a very small probability, decaying exponentially with that. Of course, more precisely, what we actually do is the following here. We still use this expression, but this chi-squared is given by this expression because this uncertainty can be correlated. And so instead of having a different uncertainty for every observable, there can be an entire correlation matrix or covariance. But other than that, the idea is basically the same. This covariance, this uncertainty must include both experimental and theoretical uncertainty. But given all of this, we can compute observables at points in parameter space. And if we compare it to experimental data, it gives us this likelihood function. But before we can calculate the posterior, which is what we want to know, we also need a prior. So what this is something that represents some knowledge or belief about the parameters that we have before we compare to these experimental data that we are comparing to in the analysis. So just a simple example from this analysis that viscosity is by definition a positive definite quantity. And so your prior will be at the very least a step function in the viscosity so that it's non-negative. But also there could be various other either physical constraints just from definition of your model, or there could be some other way of getting prior information before the analysis. But the important thing is it's completely unrelated to the exact experimental data that you're going to use in the analysis. It's prior. And just one important thing to emphasize, which I think is not appreciated, at least by everyone in our field, is that the choice of the prior is a non-trivial thing. There's not necessarily such a thing as a completely neutral or totally uninformed choice. And so we must think very carefully about this thing, because the results in principle can depend on this prior. And if it does depend, it's very important to know that and to think carefully about how it's chosen. So just an example that came up in this analysis. So there have been a couple of analyses before this work. So this is sort of a step beyond. So here's something that sort of came up. Is that so what we do? So one particular set of parameters in our model is the shear viscosity as a function of temperature, and we take it to be piecewise linear. So generally, you expect it to have some sort of minimum near the phase transition. And so we assume some structure like this, but we have parameters that allow it to vary. So the slope at low temperature and high temperature each have a parameter, and the value of the viscosity at this kink point and the position, the temperature where it occurs, are all free parameters that we use this Bayesian analysis to constrain. And so, for example, you can take each of these parameters to have a uniform prior probability. But if you do that, then if you look at the viscosity at a specific temperature, it is not uniform. So you can have one or the other uniform, but not both. So there's always something that you have to think about. In this particular case, we did take uniform probability for the parameters, but that means that our prior, which is this gray, these are some various confidence intervals. I forget which percentages, but to give you an idea of the profile of the prior distribution is already non-trivial, even before doing the analysis. So it's very important to compare the prior to the posterior to make sure that you're actually getting a constraint from the data and you're not just getting what you put in. Okay, so finally, skipping a lot of the details about the model, just a state-of-the-art simulation was used. Simulation model was used with 18 parameters listed here, including various types of things. We have a parameterized initial condition at the start of hydrodynamic evolution. We have viscous hydrodynamic evolution, including parameters for things like temperature-dependent shear viscosity, bulk viscosity, and then finally a hadron cascade afterburner. And there are actually different models for how to convert from a fluid to a particle degrees of freedom. So skipping all the details, just give them these acronyms here. And skip to some more data since we're running out of time here. So various measured observables were used from different collision systems at different energies, in particular gold-gold collisions at the relativistic heavy ion collider, lead-lead collisions at the LHC. These are observables like the number of particles, charged hadron multiplicity, also number of identified particles like pions, kaons, and protons, the mean transverse momentum, the fluctuations in that mean transverse momentum, and also the azimuthal anisotropy of these particles at various different centralities. Okay, and then skipping all the other details just to get to the final answer. This Bayesian inference procedure then gives a full 18-dimensional posterior distribution, probability distribution, which of course is very difficult to plot, in fact, difficult to analyze. So you have to also be careful about the best ways to look at it. This is just an example of taking pairs of parameters, which you can't even see, but each one of these is one parameter, and then the x-axis has the same list of parameters, and you can marginalize over 16 of the parameters to give a joint probability distribution for the two parameters. But that's a little bit hard to look at, so let's focus on these type of plots. So here we marginalize over all the parameters except those parameters involving bulk viscosity here on the left, and here we marginalize over all the parameters except those involving shear viscosity. And there's an entire probability distribution here. We just show, for example, the 90% confidence interval. So what that means in this plot is this at a particular temperature, this orange band covers 90% of the total probability of this posterior distribution after marginalizing over all of the other parameters. And this slide is just to give one more advance that was done in this analysis is realize the importance of comparing the posterior to the prior that you assumed before the analysis. So this kind of comparisons weren't done before, and so there was a lot of confusion about what's constraint coming from data and what was just coming by assumption in the analysis. So here you can see that, for example, if we're here at high temperature for shear viscosity, the prior is very close to the posterior distribution. And so the experimental data actually doesn't restrict the viscosity at these temperatures. But on the other hand, near the transition temperature, things down here, you do get a fairly significant constraint. And you can actually quantify this with information gain, but I guess I didn't put that on this slide, so we're running out of time anyway. So well, anyway, that's what these plots here. So I didn't define how to define this. This is the KL divergence between the two, the prior and the posterior distribution. That tells you how much information was gained by this analysis, but by comparing to experimental data. You didn't gain any information here, but you gained a lot here. And yeah, I guess I can quickly explain this. So this is the other advance of this analysis, that we had these different models for particleization. So it wasn't really amenable to parameterizing with some continuous parameters. So just including them in the analysis was not straightforward. But what you can do in cases like this, we have different models, is do the analysis for each model individually. And then you compare the Bayesian evidence in each case, which should tell you the relative probability of each model being correct. And by doing that, you can get results like this, that these two particular models are much more probable than this other model. And we can use this Bayesian evidence to generate an overall Bayesian model average result, which was the orange result that I showed you earlier and also here, which is just the weighted average of the posteriors weighted by their Bayesian evidence to get sort of an overall best average posterior averaging over all of the models. Okay, and I think we're coming up on an hour, so let's just conclude and then see if there's any questions. So basically, high energy collisions between heavy nuclei probe the strong interactions in extreme conditions. And there are many things that I didn't mention actually, but in this talk, I want to focus on high temperature matter, where quarks and gluons are no longer confined, the quark-gluon plasma. And although the evolution of the system can be complicated, there's many unknown things that are difficult or impossible to compute from first principles. It is possible to extract useful information from measurements. In particular here, I showed that we can confirm deconfinement, the creation of deconfined matter in these collision systems. And we can use Bayesian inference to estimate parameters. So we did this to obtain, to date, the best measurement of shear and bulk viscosity of the quark-gluon plasma to date. But probably more importantly are the better understanding of the methods, the limitations, and the better way to estimate theoretical uncertainties. And all of these advances will benefit future analyses that will be even more precise and more robust. Okay, thank you. Are there any questions? Or
thank you, Matthew, for this very nice review of the field. We can start the section of with questions now. You can raise your hands if you are watching the Zoom transmission, or use the chat of the YouTube transmission. Frédéric, please.
Hi, Matt. I have 3 questions, but maybe I should not ask all of them now to give a chance to other people. I would like to, on the second part of your talk, the Bayesian inference part, I would like to know, so the first question would be, which data did you use? And the second question would be, is there any way to get better constraint on zeta over S? So okay, I think my first question has its answer here.
So these, yeah, you probably can't see it, but these are the data. So these are measurements from Alice at the LHC. So both identified particle and charged hadron multiplicity and the transverse energy actually are all in this plot. The mean PT, V2, V3, V4, and the mean PT fluctuations. And these are measurements from STAR at RIC, which includes only a subset of these. This is the pion and kaon multiplicity, the pion kaon mean PT, and V2 and V3 of charged hadrons. So this is the data that was used. The second part is to speculate. So there are different things that are important here. One, we want to get a tighter constraint on, for example, bulk viscosity, which was what you want. But we also want an accurate, a robust estimate of the uncertainty. So just that there are other things to think about. So observables that we could add to constrain the bulk viscosity. So there are many other observables, as you know, that have been measured. And these were chosen for various reasons, but one of them is that insensitivity to things that we don't understand very well. So, for example, there was another recent analysis that used a lot of PT differential observables, and this allows you to get a much tighter result. But they didn't study at all this uncertainty due to particleization. And so actually, even though it looks like a very good tight estimation of viscosity, it actually is completely unreliable because there's a large uncertainty due to the particleization that they didn't take into account. So that's just a general comment. Wasting time so that I could think of some observables that are good for bulk viscosity. I mean, the one that is usually the most sensitive is this mean transverse momentum. So offhand, I actually can't think of the most obvious that would be best for adding for that, but it's a good question that we can discuss later. If I have more time to think, maybe we can talk about it, but it's a very interesting problem, is selecting which observables to include.
Okay, thank you. I'm going to lower my hand and I will make a question later because I see other people have questions.
Nestor, please.
Thank you, Matthew, for this nice talk. I learned a lot. Regarding the first part of your talk, what you compare with the lattice QCD, you just said these are results from simulations. What's the method of the simulation method that you're using? Does it have something to do with a Boltzmann kind of equation?
Are you talking about the lattice QCD calculation?
Yeah, you have your calculation is this blue cross, and when you're comparing it to the yellow one, that's a QCD, lattice QCD.
Yes. Which one are you asking about?
Yours.
Yes.
Your
Okay. So we did this phenomenological study doing the simulations. So the meat of the simulation is using relativistic viscous hydrodynamics. For initial conditions, we used a couple of test initial conditions. I mean, do you know anything about these details, or
no?
Should I give you model names, or should I describe
no, it's a hydrodynamics.
Idea?
You said
Yes.
that. Okay, it's
most of it's a hydrodynamics with a hadron cascade afterburner and particular models for the initial conditions.
So I was kind of worried about the transition from the hydrodynamics to the particle regime. Mm-hmm. How do you do that?
That's a good question. So this relates to the second part of my talk when we had these different models for particleization. So you need to switch from a fluid to a particle description. So you need to have some theory of some particle theory, and so the only choice, I think, or at least what we use, is a kinetic theory of Boltzmann equation description. So in this description, in the Boltzmann equation, if you are in equilibrium, then the distribution function is unique. It's well defined. It's either Bose-Einstein or Fermi-Dirac distribution. And so this is valid for ideal hydrodynamics when you are in local thermal equilibrium at every point in space-time. The difficulty comes in when you have dissipation, then you are not quite in equilibrium. And so then the distribution is no longer universal. It actually depends on microscopic details of the system. And this is actually not known very well for the hadronic system at the temperature that we need to or would like to switch from fluid to particles. So I don't know how many more details you want, but it's a kinetic description.
Okay. So this leads to the question that you mentioned the Bayesian evidence. So can you use that in order to choose your particularization model?
Yes, if you would like, yeah. If you trust everything else about the model, and you if you believe the rest of the model is very good and those are the only options for the particularization, then you definitely would just take the one that fits the data the best and use that. So that is a good example. I think
it's not only fitting the data best, but it also takes into account the number of parameters that you have in the model.
Yes, it does. It does. So yes, I agree. That's a good way in principle. I think that we're not there yet. So the particular result that I showed you, one model works better than another model. The Bayesian evidence is 5,000 times larger. But I would caution you not to take that as a final answer. But in principle, that's the idea is correct. Yes.
Thank you.
Are there more questions, Frédéric?
I see William has a question. Maybe you should talk first.
Oh, yes. Okay. Please, William. We are not listening.
Actually, you're not muted, but somehow I can't hear.
I think there is some problem. Maybe we can postpone this questions. So, Frédéric, could you please ask your questions now? Then you go back to William.
Yes, in fact, in the meantime, I had two questions, but I will ask the first one. It's very naive. In your introduction, you mentioned that it's not necessary to have a thermalized fluid to be able to talk about a fluid. I couldn't help thinking when I heard you talking about a constraint on the number of degrees of freedom. What would survive if we didn't have thermalization and we have to use a tractor and so on? So that for the first part of your talk.
So if I understand the question, at least what I would think is the most interesting, at least what I would take from it as the most interesting question is, for example, we extract this equation of state from our using our simulations from the data. So the one very interesting question for me is, if fluid dynamics still is a valid description, so these equations still describe the evolution of the energy momentum tensor, there's still a very good question of how do we interpret the equation of state in those equations? Is it the same thing as the equilibrium equation of state, or are we measuring something different? That's what I would have for me, that's one of the most interesting questions, that even if hydrodynamics is valid far from equilibrium, there's still a very interesting question of how do you interpret the parameters? So, shear viscosity in that equation, is it the same that you get from the Kubo formula, or is it something different? And the equation of state in those equations is the same as the equilibrium equation of state, or is it something different when you're away from equilibrium?
Okay, so what do we learn in this case?
Well, I mean, first we need to do a lot of studies about answering that question. In cases when you are far from equilibrium, but it still behaves as a fluid, which equation of state does it follow? Is it the same as the equilibrium or not? That's a very difficult question, but someday I hope we have a good answer to that. So far, I mean, there aren't that many systems where you can really compute, the microscopic theory, out of equilibrium without too much symmetry. So you can do it, for example, in a conformal system and do a calculation, but just because of that conformal symmetry, the equation of state is fixed in or out of equilibrium. It's always exactly the same thing. So that doesn't answer the question, but I think that is an important question, is if we have a system that's out of equilibrium and we extract fluid properties of it, how do we interpret those exactly?
Okay, we can discuss this more. The second question was with the models that you use. You have GRAD, that I know. Which are the other three? CE, for example, what is it?
So that's called Chapman-Enskog. So these are they're kind of misleading names. I mean, they both use a Chapman-Enskog expansion. But they're both basically, you do a power series expansion in either momentum or energy, and you match 14 moments to these coefficients. Whereas the others, and so what that means is that very large momentum things can go crazy, and your total particle distribution density can get negative, which is not possible. And so the other ones, which are just named after people, are two different ways of sort of exponentiating the particle distribution, the viscous correction to the particle distribution, so that it's always so the total particle distribution is always positive definite. So they're made so that they match the other ones at low momentum, and at high momentum, well, who knows what they are, but at least they're positive definite.
Okay, thanks.
William, please, do you want to ask your questions now?
I think, can you hear me now? Okay,
yes.
Sorry for the microphone problem. So I think Frederic asked partially what I was going to ask. It's about those models for particularization. For what I could understood, they are all variations of the usual Cooper-Frye that it's performed in the ideal case.
Well, I don't know what you mean. So, I mean, what you need to do is, convert from fluid to particle degrees of freedom. And in both cases, use a kinetic theory description to do that. And in all cases, you start with a equilibrium distribution, so Bose-Einstein or Fermi-Dirac distribution, plus some, actually, that's not true. So the first perturbative ones that I told you, you have the ideal plus corrections, but the exponentiation ones are different. So I'm not sure how to describe what they all have in common. I mean, they both are just methods for giving you a distribution function with input parameters being things like temperature, shear tensor, such that they match the energy momentum tensor of the fluid, so that you can do a continuous matching.
But on the end of the day, you always have to integrate this distribution function over the entire hypersurface of a given, obeying some given criteria.
That's right. So anything that you measure is not local in space, because this freeze-out surface is microscopic and the experimental detectors are far, far away. So the only thing you can measure are things that are integrated over the entire spatial surface, even though the formulas are local to the surface.
Okay. And a second question, perhaps that's a bit naive. But when we have the results that we have the book viscosity is not unconstrained for high temperature, is that a limitation of the of Bayesian estimation that cannot clearly constrain it, or is actually a physical minimum that the parameters that we are inputting are not actually sensitive to book viscosity at high temperature?
So I would say we have pretty good evidence that this is due to, well, I mean, it's due to the whole system, but I think specifically the observables that we use to do the analysis are not sensitive to the viscosities in this temperature region. So if you could change the viscosity at high temperature, and these observables would not change very much. It's possible that if we choose other observables, you would get a higher sensitivity. It's also possible that essentially nothing depends on these high temperatures. But I would at least look at other observables if we wanted to try to constrain these higher temperatures.
Okay. Okay. Thank you.
Thank you, Matthew. I have one last question. It concerns this Van Hove's law that you mentioned. Is this a thermodynamical law? What exactly it is? How it was proved by Van Hove, or it was just proposed from other things?
Yes, not proven at all. It's just a conjecture, a sort of an idea. So it's very qualitative, but let's see if I can go back. Oh, how far back is it? Yeah, it was just a qualitative proposal in this paper that, somehow both the mean transverse momentum and the temperature have something to do with the energy per particle, and so there might be some sort of proportionality, and of course entropy should have something to do with particle number, which is also very, very straightforward. But there's no mathematical proof, and in fact, it's not. It's not precisely true in any particular approximation.
I see.
But it's approximately true in our case, so that's good.
Okay. Thank you. Are there more questions, Frédéric, perhaps?
No, thank you.
Okay, then I think we can finish the sections of questions now. And thank you very much, Matthew, for this very nice talk. We learned a lot about your field of research. Again, we meet next week, next Monday, for another talk, also on particle physics. So, bye-bye. Thank you.
Obrigado. Tchau.
Marcelo, já podemos fechar, viu?